Let's take a closer look at the first advantage of our feedback amplifier, improved gain sensitivity. So we're going to start with equation 5 from our previous video. And so what we're going to do is we're going to assume that our feedback transfer function beta is constant. And we're going to want to take the derivative of equation 5 with respect to our A. Derivative of our equation 5 with respect to our open loop gain A. And so what that's going to do, if we think about it, is we're saying DAF, what are the changes in our closed loop gain with respect to changes in our open loop gain? So ultimately we're asking this question if we have some transistor parameter that's varying and that causes our open loop gain to vary on our amplifier, how much is our closed loop gain of our feedback system going to change? And so we can, of course, use this equation 5. So we're going to say this is the derivative with respect to A of A times 1 plus beta A to the power of -1. So I've just written it slightly differently. And so what we're going to want to use here is our product rule. So we can go through and we can say this is going to be DAF with respect to A. And so if we do the product rule, we get A times 1 plus beta A to the -2 times negative beta. And then for the second part, we get 1 plus beta A to the -1 times 1. So combining all of that together, we're going to have our first fraction is going to be negative A beta divided by 1 plus beta A squared, so that whole quantity squared. And our second term is just going to be 1 over 1 plus beta A. Well, so now what we're going to do is we're going to want to combine these into one fraction. So let's get a common denominator of quantity 1 plus beta A squared. And so we just have this negative A beta from the first term. And now our second term, of course, we have to multiply top and bottom by 1 plus beta. So we're going to have, 1 plus beta A. So we have something that looks like this. And so what we notice here is in our numerator, we have negative A beta and positive A beta, which are going to cancel out. And we're going to be left with just 1 over 1 plus beta A quantity squared. Okay, so now we're going to play some games with this to make it a little more useful. So we're going to move this dA to the right side, and we're going to divide both sides by AF. So let's move this guy over here to this side, and then we're going to divide both sides by AF. Okay, and so what that's going to give us is on the left we still have our DAF, and so now we're dividing both sides by AF, so let's go ahead and do it on the left side. And so we can see what this is going to be is our percentage change in our closed loop gain. Okay, so now let's look at our right side. So we have our dA, which we've moved over here to the right side, and that is divided by this 1 plus beta A squared, which we had from the previous line. Now we're going to divide by AF. We divided by AF on the left, we need to do it on the right. But instead of just putting AF, I'm going to put our form that we had before. A divided by 1 plus beta A. So this is what we had from up here in equation 5. So from this, we can see that this 1 plus beta A in the denominator is going to cancel out with one of our 1 plus beta A's up here. And so what we can see is this is then going to simplify to 1 divided by 1 plus beta A times dA divided by A. And so now we can see we're relating our percent change in our closed loop gain to the percent change in our open loop gain. And so we could also write this as AF divided by A times dA over A. And so it's worth noting that in the notes this is how I have it written, but we probably should specify some kind of A prime here or something, just to indicate that this is the original AF. original closed loop gain, AF. Okay, but if you want to be careful, we can just use this function here, or this expression, and then in the next video we're going to come back and look at an example. And so what we can see, just by sort of comparing these two areas circled in purple, we see that our percent change for our closed loop, so percent change for our closed loop gain, A sub f, is smaller than the percent change in our open loop gain, A, by this factor of 1 plus beta over A. And so again, this change in A is arising from changes in individual transistor parameters. And so this term 1 plus beta over A actually has a name as well. So I know what you're thinking, not enough names. So we'll try our best to add as many as we can, is basically what we're doing here. So our 1 plus beta A is actually called our desensitivity factor. So in our next video, we're going to come back and we're going to see how we can put this equation into use. And ultimately, we're going to see just how good of a job this feedback network does of decreasing sensitivity of our gain.